Okay, so in this video, I'll explain what the first variation to a functional is, which in the last video I said was sort of analogous to the derivative of a function. And I'll try to explain why that is useful in finding an extreme value of the functional. So the way I'll set up the video is I'll first explain like the procedure to find an extreme value for a function in the usual one-dimensional case with differential calculus. And then I'll draw analogs of each of those steps into the calculus of variations. And so I call all of that abstract garbage because it's just going to be a bunch of symbols floating around. So if you don't understand all that, in the second part of the video, I'll derive what's called the Euler-Lagrange equation, which is the equation that you usually use to solve these variational problems. And with that, alongside that, I'll try to solve the problem of between 2 points, what curve will optimize the length between them. And hopefully that'll give a better explanation. So I'd recommend watch the first part of the video, and if you don't completely understand that, watch the second part, and then after you have some concrete idea of what I'm saying, go back to the beginning and watch the first part of it again. So as a reminder, what would be a functional? So if you have a graph, so this is your x-axis, and you have A and B, and for now we'll fix the endpoints, so you have 2 points A comma A and B comma B, and you have some function y of x. Then you have for now you have some functional j of y, which is equal to the integral from A to B of f of x y prime dx, where f is just some function of 3 variables. And for example, we saw that if you have the integral from A to B of y dx, this will represent the area between this function and the x-axis. Or if you have the integral from A to B of root 1 plus y prime squared dx, this will represent the length of your curve. And so we'll be looking at this in the second half of the video. And so our idea is we want to find something associated to this called the first variation. And using that first variation, we'll set the first variation equal to 0, which is analogous to setting the derivative of a function equal to 0. And that'll allow us to find extreme values of our functionals. And so now I'll explain sort of in detail how you do that in the one-dimensional differential calculus one variable case. So in calculus, you have some function f of x. And so I'll just draw this out again. So this is your x, y, and this is some function f of x. And you want to find extreme values of this function. So for example, this is a minimum, and this up here is a maximum. And so you should know that to find that out, what you do is you find f prime of x, and you set that equal to 0, and then you solve for this value of x. And then that value of x is hopefully an extreme value of your function. So this is actually not a sufficient condition. So that means that if this is solved, it's not necessarily a maximum or a minimum. For example, you can have something that looks like this, which is y equals x cubed. And over here, the derivative is equal to 0, but that's neither a maximum nor a minimum. But the idea is that this usually reduces the amount of points that you're working to a very small number of points. And once you get those small number of points, you can sort of check each one individually and figure it out. So what is f prime of x? So f prime of x, you should know, is the limit as h approaches 0 of f of x plus h minus f of x over h. But what I'm going to think of is not like this definition of the derivative, but instead a sort of definition which is dependent on what the derivative actually represents. So what I'm going to say is, let's say that we have some f of x naught plus h. So x naught is some fixed value, which, for example, this would be our extreme value that we're trying to find. And we're sort of changing it a little bit. So if this is your x naught, then x naught plus h would be this point. Or x naught plus h would be its coordinate at that point. And so you want to look at what the output is. So this is equal to f of x naught. By Taylor's theorem, this is equal to f of x naught plus h f prime of x naught plus h squared over 2 f double prime of x naught plus h cubed over 6 f triple prime of x naught. And so this is one way to write down Taylor's theorem, which is expanding a function around a point with its derivatives. And the idea is that if h is really small, then these values will be even smaller. And so this value will dominate, and this essentially gives you a formula for the tangent line to occur if you just take the first two values. And these higher order terms, you can also write that as h times epsilon of x naught comma h. So epsilon would be h over 2 f double prime of x naught plus the other terms. And so this, I'm just writing it this way because we'll also do that something similar on this side. So anyway, how is this supposed to help us find an extreme value of our function? Well, as I said, if h is small, then f of x naught plus h is roughly equal to f of x naught plus h f prime of x naught. So what does it mean, for example, for a value to be a minimum? So let's look at a zoomed in example here. So let's say that this is your function and this is your minimum of your function, right? So what it means to be a minimum is you take some small interval around your x coordinates. And so if you look at this point, which is x naught plus h, f of x naught plus h, this would be some other point. And the idea is that the y coordinate increases, right? So this is your point x naught comma f of x naught. So for h small, you want, or for all h small, so this upside down a just means for all. So for all small values of h, you want f of x naught plus h minus f of x is greater, or f of x naught is greater than or equal to 0. This means that x naught is a minimum of f. And notice that this is even true if h is negative. So like if h is negative, then you have a point back here. And so we want to look at how this will help us in finding that. So since we are looking for f of x0 plus h minus f of x0, it makes sense to sort of subtract this from both sides. So we have that f of x0 plus h minus f of x0 is approximately equal to h times f prime of x0. So the way to interpret this is that this is sort of your vertical displacement, and this is, you can think of this as like h being sort of change in the x-axis, and f prime of x0 is like your slope of the tangent line. So this is approximately equal to like your displacement times your tangent line. So if you have a function that looks more like this, and you consider this point to be x0, then this will be x0 plus h is your x coordinate, and your y coordinate change is approximately delta x times your slope, which will be delta y. So your delta x is h. This will be your delta f, which will be f of x naught plus h minus f of x naught. And then this will be your slope, which is the slope of the line. So I just want to point that out purely because this is the quantity which over here will be the first variation. Not just f prime of x0, but the whole h times f prime of x0. So if h is really small, right, then this whole series, let's say h is 1 over 1000, this will be roughly on the order of at least 1 over 1000 squared. And that means that the sign of this will be approximately the sign of h times f prime of x0. So if like this is f of x0 and this, the h prime of f of x0, h times f prime of x0 increases by this much, then if h is really small, then h squared times your other terms, or like h times epsilon, will only affect it by this much. So the sign of this is going to be the same as the sign of your right side. So let's look at what happens if f prime of x0 is non-zero like it is over here. So let's assume f prime of x0 is not equal to 0. And so if we take a small increment to the right, in this case, then that will mean that f of x0 plus h is f of x0. Let's say for simplicity that f prime is greater than 0. Right? This is going to be equal to, or approximately equal to, h times f prime of x0. And at least it'll have the same sign, and we only care about the sign here because that's what we care about in this case. So if f prime of x is greater than 0 and h is some positive value, like moving to the right in this case, then this is going to be greater than 0. However, if you look at f of x0 minus h minus f of x0, so this is the same thing as up here, except you're changing the sign of h. So that means on the right side you should also have the same expression, except you're switching the sign of h. So this is approximately equal to negative h f prime of x0, which will be less than 0, because this quantity is positive by assumption, and negative h is moving to the left. So graphically what that means is that you choose some point to the left. This will be x0 minus h. And then if you notice here, the h times f prime of x0 would be this change over here, which is approximately equal to your change in your actual function. And here, if you move to the right, you're moving up, but if you move to the left, you're moving down. And so that means that this cannot possibly be a minimum. So you can do a similar sort of analysis if f prime of x0 is negative, which will mean that this first quantity is negative and the second quantity is positive, right? And so again, that means that you can't have a minimum because this does not hold for all h in a small interval. And so that means that a necessary condition for x0 to be a minimum is that f prime of x0 times h is equal to 0 for all h small. So like for all small values of h. And so I have this whole quantity is equal to 0 for all small values of h instead of f prime of x0 is equal to 0, because that's what we'll be working with here. But it's pretty easy to see that if this is equal to 0 for all values of h, then that must imply that f prime of x0 is equal to 0, which is just your usual condition that you have in calculus. So now we're going to draw analogs to everything that we have here onto this side. So we're going to assume that here we're really looking for an expression of f of x0 plus h minus f of x0, right? So we're going to look for an expression that looks like j of y0 plus h minus j of y0. And so here, for example, this is your original function y0, right? And you can sort of vary this a little bit by some quantity, and this new curve you can call y0 plus h, and h is a function of x again. And so here, it sort of makes sense intuitively what h of x is small means. That means that your new curve is very close to your original curve. And to be formal about that, I would have to introduce like functions as being a vector space and introduce a norm on that. But I want to leave that off because I want to get to the juice of the math first, because that's more interesting. And maybe I'll make some supplementary videos talking about like the nitty-gritty details. So anyway, what you want to do is you want to express this as being equal to some j prime of y0 comma h plus epsilon of y0 comma h times, again, this is like your size of h. Don't worry too much about this. But the idea is that epsilon goes to 0 as size of h goes to 0. And the size of h you can think of as being the maximum over x in your interval ab of your magnitude of h of x. So this is like some of the more detailed stuff, but the idea is that this epsilon sort of represents your higher order terms, and then times the size of h means that these terms go down at least as fast as like second order in h. So for example, this term goes down as fast as second order in h, this term goes down third order in h, and so on. And so these terms go down really quickly. And what that means is that if h is small, So again, intuitively, that just means that you have your original curve and you have some curve that is slightly different from that. And you're looking at, for example, this would represent the arc length of your varied curve. This would represent your arc length of your original curve. And you want to say that that's approximately equal to something plus some small terms that don't matter. And so you want to figure out what this is. And so we say that for h small, j of y0 plus h minus j of y0 is approximately equal to j prime of y0 comma h. Now here, we're going to sort of take y0 to be sort of in the background. It's like an implied thing. So we're going to rewrite j prime of y0 comma h as being delta j of h. And so what delta j is it would be the analog of this whole expression here. So this you can think of as delta f of h. And so this does obviously depend on x here because it depends on what point you're looking at. But really, as we saw down here, we're changing up the properties of like if you're incrementing to the right or if you're incrementing to the left. So you want to pay attention to like the properties of this h. So you want to sort of think about more of the properties of the h than the x0. And solving that this is equal to 0, which is f prime of x0 times h is equal to 0, actually gives you the condition on what x0 needs to be, which is f prime of x0 is equal to 0. So it's the same sort of idea that we'll have here. And it turns out that delta j of alpha h, where alpha is some real number, is always equal to alpha delta j of h, and delta j of h1 plus h2 is equal to delta j of h1 plus delta j of h2. And so this says that if you change your function once to make this like y0 plus h1 of x, and then you change the function again a little bit to make this sort of y0 plus h2 of x, then to the first order, this will approximately be equal to the sum of them. And that makes sense here as well, because if you change this to like scaling h up by some value ah, so that'd be like ah f prime of x0, then this is your delta f of h times a, or you can sort of consider it by bracketing these two terms together, which is delta j of ah. And on the other hand, if you sort of increment it twice, so if you take this as your x0, and then you increment it to x0 plus h1, and then increment it again to x0 plus h1 plus h2. Then looking at this expression again, you can easily see that delta f of h1 plus h2 is equal to delta f of h1 plus delta f of h2. So this property won't be useful for now. I think I'll make a second video on that. And this is pretty much to show that your thing is unique. But this will be the property that will be important to us, which is that this scales linearly with alpha. So this is more of like the abstract arcs that I was talking about. It's just a bunch of symbols. So when I go through the actual examples, hopefully this stuff will make more sense. But anyway, moving forward, we want to say that this is approximately equal to delta j of h. So let's say that we have, for some h, delta j of h is greater than 0, right? What that'll mean is that j of y0 plus h minus j of y0 is approximately equal to delta j of h. Oh, I forgot to say what an actual extreme value of this is. So an extreme value, analogously to here, extreme value of your functional is a function y0 of x such that for small h, j of y0 plus h minus j of y0 is greater than or equal to 0. So this will mean that y0 is a minimum. So this means that if you vary your curve by a little bit, then the value of functional will change. So for example, the optimum value here is obviously a straight line for the length of the curve. So that means that if you vary the length of the curve by a little bit, then the length of that curve will increase. Anyway, so moving back to this, if this is true, then we can, this quantity will be greater than 0. However, if we sort of change it and we use the opposite sign, so j of y0 minus h minus j of y0 is approximately equal to delta j minus h. And so now we can use this property with alpha equals minus 1 to rewrite this as negative delta j of h. And this will be less than 0 because delta j is greater than 0. So what that means is that if you vary it in one direction, it'll be longer. But if you vary it in the other direction, it'll be smaller. And so you can't have a minimum. And to graphically explain this, let's erase all that. Let's again consider that you have 2 points, A, and B. So let's consider like a parabola sort of a thing here. And we're talking about arc length. So if you change the parabola a little bit to look like that, so this is your y0, this will be your y0 plus h. Then notice that the arc length of this new thing is smaller, just visually. However, if you change it in the other direction, this will be y0 minus h. So like each point you sort of move it down instead of moving it up. And you have the same sort of, not variation, but augmentation of your original function. Then here the arc length will increase. So obviously y0 can't be an optimum value, because if you change it by a small width and by a small amount in one direction, the arc length decreases, but in the other direction it increases. On the other hand, if you consider a line between 2 points, right, then if you change it by a little amount in one direction, so this will be y0 plus h, or if you change it by a little amount in the other direction, y0 minus h, then the length of both of these things will be larger than the length of your optimal thing. And that is equivalent to saying, finally, that delta j of h is equal to 0 for all small h. And this will allow us to derive the Euler-Lagrange equation, which we can use to solve for what our optimal value y0 should be. And in the errata video, again, I'll show that if this is true for any h, then it's true for arbitrarily small values of h. So you can actually say that this is equal to 0 for all values of h. And yeah, now I'll finally get out of this abstract garbage and explain optimizing this value and solving the Euler-Lagrange equation.